Okay, so let's continue with the session. So let me introduce our next speaker. It's a pleasure to introduce Professor Giancarlo Urzúa, who is talking about degenerations of the Pezzo surfaces with only Wahl singularities.
Okay. Okay, so this is a work joined with. Thank you very much for the invitation to come here. Glad to be back in Miami. My first time was 2 months ago. So this is a joint work with Juan Pablo Zúñiga, which is a PhD student of mine in Univ, Chile. I work in Santiago, in Chile. So this is going to be about the generations of the Pezzo surfaces with only Wahl singularities. I will introduce these Wahl singularities in a moment. And maybe you know what the Pezzo surface is, but just in case, so this is P2, this is P1 plus P1, and then draw up the E point of P2, where E goes from 1 to 8, general position. Del Pezzo. Okay, so the situation is you have a family over a disk, belongs to disk, and then on the general fiber you have this Del Pezzo, degree D. So the degree is just the self-intersection of canonical class. And this degeneration is Q-Gaussian style. And then you have a singular surface. Normal projective surface. Complex with only Wahl singular. And the idea is to classify all these situations. Okay. So let me tell you motivation. So motivation came from a research paper by Polishuk. Grains. 2004, 2024, and they have the following results. Here in 1A. So for Del Pezzo, 4 degree, 4 Del Pezzo surfaces, and any integers delta and R, but R must be bigger than 0 for prime. Then there exists an exceptional collection of 2 terms. So E O of the Del Pezzo surface, exceptional collection, where rank of E is equal to, okay, sorry, let me change it to N, and C1 E dot minus K, which is the degree of the vector bundle. This is an exceptional vector bundle. This is O, square of G. This gives you exactly that. So complete freedom on this kind of situation. And also they have this theorem B, where they say if degree is bigger or equal than 5, then not every slope, or slope in the sense of delta over n, is possible. Actually, infinitely many are not possible on the Pezzos of that degree. Okay. So that was motivation for us to start studying these kind of things. Why is that? Because of this philosophy of Paul hacking that was mentioned in the first talk. So Paul's philosophy. Says that if you have a solemnity X, this is a smooth projected surface complex. The surface, a singular surface with so H1 OX, so irregularity, and H2 OX equal to 0. Then we should have a situation like this. For E exceptional vector bundle on X with rank N and C1 E dot K congruent to A mod N. If you look at the set of this kind of vector bundles, that should be in a sort of correspondence with degenerations. So X is in a family over this, like here, the Lorentz time, generating the surface W with one singularity. So this is a normal projected surface with one singularity, and the singularity is a Wahl singularity. So what is that? 1 over n squared. So Cn. And then the exponents are 1 from normalized and a minus 1. So if you have a situation like this, that is maybe because you have a degeneration like that, and if you have a degeneration like this, plus some hypothesis, there is something might going on here, you should have an exceptional vector bundle. This is a construction by Paul Hack, and that is kind of the way why you have this kind of a way to explain why you have this kind of degenerations for a non-singular projected surface. Okay. So these are called, so the way this goes is that if you have a situation like this, plus certain hypothesis, you construct what we call hacking bundle. So this is maybe 2012, something like that. Okay, so according to that philosophy, if you look at theorem A and B, then this is saying, so maybe, and this works perfectly for the Pezzo surface. So anytime that you have a degeneration of a Pezzo surface with this type of singularities, so you know this type of singularities, these are the cyclic quotient singularities of the order and so on. So if you have degeneration like that, for the Pezzo, this is like a 1-to-1, up to tensoring by line bundles and dualizing. Okay. So theorem A plus theorem B should be saying so A for the Pezzo surfaces of degree 4, we don't have any restriction on the type of degeneration. So degree 4, then any Wahl singularity should be possible. I mean, these people do it in another way. This is something that has to be checked. Okay. So for any degree, so for degree 4, any Wahl singularity should be possible in a degeneration. That is what they claim. And B, for degree bigger or equal than 5, then if so that there are restrictions, not everything is possible. And then, okay, we started to study this. So maybe I want to give you an example that was also mentioned. Somebody mentioned Oracle. Used to be here. It's in the back. So example of P2. So we know complete answer for when WT is P2 for this question that I mentioned here. If degree is 9, the same as P2, we have complete answer. So for degree 9, yeah, P2C. P2 is a rigid surface. You cannot really change it into a non-singular surfaces, but you can degenerate, and that has been classified. So it is complete answer. And this is after, let me say, Badescu, Manetti, and Hacking again, last program. And this is 2010. And the theorem says that if you have P2 generate into W, say that the singularities for this normal surface are log terminal. And that means in dimension 2, quotient singularity. Okay. With LP singularities. Then this is if and only if W is a partial Gorenstein smoothing of the projective plane with weight A squared, B squared, C squared, where A squared plus B squared plus C squared is 3ABC. This is Markov or Markov equation that shows up in many places in mathematics. Very strange. So we know, so when you have a triple like this, we call it Markov triple, and we know all solutions. There is a very famous conjecture about the triples. There is a lot going on. This is like another talk, but I will keep going. Is this understandable? So how do you get W? For this surface, you have 3 singularities. It happens that if you satisfy the Markov equation, all of them are Wahl singularities. And then this W is a partial smoothing of maybe this singularity or this and this. In all of them, then you get P2 back.
And that's all the scatter diagram I mentioned.
Yeah. We actually have a paper with the same guy, Juan Pablo Zúñiga, about the birational geometry of Markov numbers. Okay. Okay. Now I will move to in general. So at the end of the talk, I will come back to theorems A and B, how to prove those theorems using degeneration. This is actually super simple, and this requires something. We should start 11, 10. Yeah. Okay, so I am interested in this kind of degenerations in general. W will only, so as before, so this is Lorentz type. But now, in general, I mean, any situation, WT today is at the Pezzo surface, but typically I work with surfaces of general type and the same situation. Okay. And even so, and also, so this here you have Wahl singularities only. And you know that if you think about terminal singularities with a Milnor number equal to 0 smoothing, sometimes they are called QHE singularity. Then this implies that they are Wahl singularity. It's another way to define them. But there are more. There are more. And I am also considering these other QHD singularities, which are not even log canonic. Okay, there are big families. And there is actually a conjecture by Jonathan Wall that any QHD singularity is weighted homogeneous. And if that is true, then we really know all of them, that they were classified by Upal. And here I'm step 6. You know this person very well, right? But I don't remember how to spell it. 1000 something. Yeah, right? So there is at least big family. And some of them are this Wahl singularity. I am also interested in this kind of situations, even though they are not canonical. I just wanted to mention that. And so all of this means mildest possible degeneration. So no vanishing cycles. Like almost working with a smooth surface. And my main goal, that program, is to classify every single surface W and then tell you if they can be smoothable to WTs or not. So, mainly those. One, classify all possible W's under no restriction. For given canonical intersection of the canonical class, and maybe the typical invariance like PG and Q, the Euler characteristic of O. And 2, classify the smoothable W's from 1. Okay, in these main goals, the hardest are general type. So when canonical class of W, canonical class of W is big. And then, for example, you have, using this type of surfaces, you have these exotic blow-ups of P2, and there are many open questions about that, and it's so hard to work on them. Recently, we were able to classify the case of Horikawa surfaces, and I will not talk about that maybe. And so on. This is very, very hard. Observation. So today is not going to be this, it's going to be today is the opposite. minus canonical class of W is the. But I want to do some observations since I was in the first talk. So there is an explicit MMP on these families. And what I mean, again, this kind of situation, and that is relative to canonical class. You know when you run MMP, you need to say MMP with respect to what? This is canonical class. And this is explicit. And this is my work with for hacking in Junior Develop. That was published 2017. But of course, after more for that. Okay, so using that, when you work with canonical class B, then you may work with canonical class B and H. Why is that? Because when you have a situation like this, we run MMP, and all the time when you perform these flips or divisorial contractions, you keep this kind of information. So you never leave this category. So if you have a smooth fiber, you have equivalent sign smoothing of a surface W with only one singularity. And so if somehow if the certain intersection of canonical class is negative, you can make it positive after a finite amount of flips and divisorial contractions, which are very explicit. Another observation is that these usually this kind of degeneration produce not only exceptional vector bundles on WD, but exceptional collection. Collections of vector bundles. And this is my recent work with Genia, 2022. And in particular, you know, when you have an exceptional collection, then you have a semi-orthogonal decomposition of the right category of this WD. And you have several exceptional objects that you might mutate the previous one. So these mutations are geometric. This is birational geometry, and we describe the birational geometry of that. The mutation of them are reflected in explicit birational operations like clips, flops, serial contractions that come from the previous observation. So for example, when you have, say that you have a cyclic quotient singularity, and this is one of the main results in that paper. Now I'm talking about that just because of the first talk. Maybe one. An example. Now, if you take a cyclic quotient singularity, and you have a deformation of this, so say, like this, so this is the cyclic quotient singularity. You know that there are several ways to deform, as many as the Catalan number in general. Many ways to deform. But to even smooth. But control by what is called the polar Sheffer-Barron correspondence. And in that correspondence, for each irreducible component of the deformation space, you have a partial resolution of the singularity that has only Wahl singularities. You do the Kuborenstein smoothing of those, you get a smooth fiber, and then you blow down that deformation, and you recover this. Irreducible components of deformation space in one-to-one with this kind of degenerations, but the partial resolutions that are positive with respect to canonical class. We originally they were called P resolutions, but with Wahl singularities we call them M resolutions, because with P resolutions the relative canonical class is ample. M resolutions means NEF. So maybe you have some zero curve with respect to canonical class. M resolution. And this has to do with continuous fractions of zero, of the dual fraction corresponding to the singularity. But now with Genia, we came up with these M resolutions. M resolution, which is a kind of negative analog of M resolution. This is positive, this is negative, but negative analogs are infinitely many. But then for each of them, you have these decompositions given by exceptional vector bundles. I don't know, 0 up to ER. Let me put it like this. So this is the amount of singularities that you have in the M resolution. And here you have the same thing, but for the corresponding vector bundle. Okay. And one can prove that the part of the derived category corresponding to these vector bundles is the derived category of a Fourier of the modules of a particular Fourier algebra, and they look like this, and with no relations. So if you have R points, so let me do it for 3 points. But in general, you have as many points as exceptional vector bundle. So with 3 points, you see something like this. So only arrows from left to right. Okay, that is the comment, just to connect, to make a connection. So later maybe okay, so now coming back to the Pezzo generations. Today, over with that. So today, as I said, canonical class of W. So by the way, when you have a degeneration, this kind of degeneration, the self-intersection of canonical class is constant.
Very quickly ask that. There's the sectional collection that happens on the smooth.
Yes. So on the smooth, there is also one on the singular guy, and there is also one on the threefold.
Yeah, it's actually totally related. So you can take that. That's a Fano surface. Yeah.
Mhm.
You take the total space of the canonical bundle of that.
Mhm.
That's the Calabi-Yau 3, and those objects gives you the simple objects in the Calabi-Yau 3. So it's actually
Okay.
connected to my storage.
Yeah. Okay, so today this is E bigger than 0 and minus canonical class B. Okay, so I would like to say that here, I just said in here that the canonical class is B, and maybe the self-intersection is negative, and then you run them P to get it positive, and so you have big net. And here, if you run MMP, then you arrive to very trivial situations. So we don't run it. Okay, we keep it as it is. When you have a degeneration of P2, there is no running MMP. And you can blow up a point, like a section, then you have a new situation, and you can run MMP in that new situation. That is the topic of my paper by rational geometry of Markov. But in here, I will not do that. And also, I have to say, if this is 0, or if this is negative, that is very interesting situation. That might be related to Nagata conjugation and things like that, related to that thing. So this is very bigger than 0. So if we have bigger than 0, then we have a theorem. So far, we don't have for 0 or for negative self-intersections of canonical class. So the situation is the following. And if you have the minus canonical class is big, then W has no local to global obstructions to the form. So that is very good. You know, in principle, you always have W that you want to classify with this invariance, and then you need to do something else to prove that it is smooth. Sometimes they are not. But here is for free. So you can do whatever you want with this Wahl singularity. We take the mu equals 0 smooth. Okay, so we always have. So we have moving, and we take the general one, so that under this condition, now this is the best degree D. Okay, since we have no obstructions, we can consider also a situation with only one singularity. So you have many singularities here. We smooth them all up to 1. So we have this W star. And we really, instead of classifying this W, we want to classify the W star. The situation with only one Wahl singularity. And the question is, depending on B, what can we say about the Wahl singularities that appear? Okay, that is a mystery. For degree 9, only this Markov singularities. What we prove, yeah, this is me and Zúñiga. This here is that there is another. So given situation like this, there is another surface that we call W star M, because this is Mark surface. This is Mark surface. So that we need to do maybe some blow-ups. And then this surface is a degeneration of that. So we understand completely, if we understand completely this one, then we have control on what can happen. The singularity here is the same singularity. So this has only one singularity, and it's the same. But when you have a when you have a Wahl singularity, to have a certain degree, then you need to mark the singularity. I will tell you how, and that is why this is called marked surface. They are all del Pezzo. These are del Pezzo, and so these are del Pezzo that are degenerated. I will be more precise at the end of the talk, okay? But this is the idea. Let me do it for P2, since that is easier, and with very concrete example. So there is a beautiful combinatorics behind this, which I was going to explain, but then I said, no, too much. Just one talk. So crazy continuous fractions and definitions. So I'm not doing that. I will explain you an example. So back to Harte. So very very concrete. Let us take that this is a Markov triple. Okay, and so and I take the corresponding weighted projective plane. I will take a equivalence time of the singularity corresponding to A and to B, and I will keep C. Okay. So here you have this W star, mentioned there, with only one singularity, 1 over C squared, A squared, B squared. This is a Wahl singularity. Okay, I consider the minimum resolution of this. And this is the key part to have control. I need water. So dry. To have control on the singularity. Okay, so the situation is like this. We have, you know, when you resolve a single quotient singularity, there is a chain of P1s.
Can you draw that toric picture?
Yeah, I'll do that. So for the singularity, it's something like this. So minus E1, minus E2, minus ER. And so let me change this to 1 over n squared, n is C. Unfortunately here, I would like to say A, but A is taken. Stop. A, B, C, E, E. And so, you know.
This is like the purpose resolution of the singularity?
Yeah, this is a minimal resolution, so EIs are all bigger or equal than 2. And this is the Hirschenberg-Jung continuous fraction. You write it like this. Okay. This is what I call Wahl chain. So now I draw it here. And there is a particular curve that would be like a section in here. Yeah. So some position here would be like a section. Here you have a P1 fibration. And now here you have the rest of the exceptional divisor. Like that. Minus E1, minus ER, and you know, like this. Like that. And there are two minus 1 curves somewhere that are marking on one fiber and on the other. Okay, that is the situation. Then, if you contract the blue and continue, you will get a fiber. So you will go to 0, 0, and try and avoid to change the self-intersection of this curve. So this is going to be minus EI. So this is a P1 fibration with this section. This is the Hirschenberg EI surface. Okay. In this case, there is an accident. EI has to be 10. It is very simple to prove, but I will not do it. Okay. Okay, so I want to take that example. Also, you have the situation where when A is equal to 1, so you have two singularities. And then what you see is a section like this, and something like that, but there is no other fiber. Then the self-intersection of this curve is minus 7. So you get 10 or 7. But this is very particular of P2. One more concrete example of the same thing. Take the Markov number n equals 29. A here is, I put it E, is 22. Now you write the continuous fraction like this. Then this is the 10th in the center. And then 2 times the 2. And you are marking like this. So you are subtracting if you want here and here. So when you subtract, you know, you go down this minus 1/3. From here you will get 2, 1, 2, and you keep going and you will get 0. Subtraction. If you do the same here, you get 2, 2, 2, 2, 1, 5. Keep going and you get 0. So this is the combinatorial way to think about a word chain that corresponds to degree 9 degeneration. You know, this is a way to combinatorially think about the Pezzo surfaces. You only need word chain in a situation like that. So it turns out that to prove this theorem, we realized that exactly the same happens for any degree. So I will explain that. I have it here. Just in here. So you see here you have the word chain. This is the word chain. And I'm marking 9 as the central curve. And then there are some markings to create a zero continuous fraction on the left, zero continuous fraction on the right.
Is 8 plus 1.
What?
This is BPA. This is like one blow up of CP2, or
Each one is one block of CBT.
no, I mean the 10 there, P2 is the base of degree 9,
Yes.
right? In degree 8 we have P1 times P1 or one blow up.
Yes. Okay, that is your question.
Right.
This is degree 7.
Oh.
So here A squared is degree 7. For degree 8, as you say, we need to choose. We have at 1 point for P1 plus P1, and we know how to choose according to the combinatorial data. Maybe I will mention it. And in degree, this is degree 7. As you see, these are the markings. So you have here 1, 7, smart, 2 smart, and on the other side is smart. So you subtract here 1, you subtract here 1, you subtract here 1, and this continuous fraction here is going to be zero continuous fraction. You can completely contract it to a situation of a P15. The same with the other. Okay, and the geometric situation is like this, starting of course with F9. And there is a bunch of blow-ups to right.
What's the combinatorial relation of the 9 and the 7?
Yeah, so I can write it down here. That is the thing that I was trying to avoid. So, you know, we have this definition of a word chain. A word chain is the Pezzo of degree D if so a word chain E1 up to ER. And then you have two types. The first type is E2 ER or E1 ER minus 1. Admit a zero chain of weight lambda. That means, I will explain that. That means, so there is a way to mark in here, so that when you subtract the marking, then you get a zero continuous fraction, and the weight is exactly so when you mark with certain numbers, di. So now the weight is lambda plus 1 equal the sum of the di. This is how you compute this way. So, example here, the weight is 0. Here is the weight is 0. That means that this is the dual of a wall chain. So this is a dual of a wall chain, and here you have a wall chain. And because of that, you get that this number is 10. But in general, it's much harder. Okay, so you have that. But there are also type 2, like in that board, where you need to choose an I between 2. I mean, there exists a position I between 2 and R minus 1, so that E1 to E minus 1 and EI plus 1 and ER admit 0 chains, each of them of weight lambda 1 and lambda 2. And this lambda is smaller or equal than 8, and here both smaller or equal than, so that the sum smaller or equal than 8. And why is that? Because the degree then is computed as 9 minus lambda, or 9 minus lambda 1 plus lambda 2. This is the degree. So in that case, you have 3 markings. You need to subtract 1, then you get 2 for lambda. This is lambda 1 is 2, and here lambda 2 is 0. Then 9 minus 2 minus 0, 7. This is degree 7. Okay, so I want to finish. I will finish with the theorem. But here is something, when you have these two, you have this situation with one Wahl singularity. Like that. This is my mark. But in this case, this is always a marked circle. And this degenerates to a projective plane with weights. And here we get the same. So how you do it? The following. We call it sliding. And this has to do with mutations. So these are the slidings of the blue marking curves. The blue marking curves are this minus 1 curve. What you do, so imagine that you contract this minus 1, so you have a point here. And now this point, you move it up to this intersection. And now there is a bunch of blow-ups, so that you recover exactly this wall chain and another, and some other wall chain appears. So you have another wall chain at the beginning, which is exactly this, and this other marker somewhere, where exactly maybe. They appear somewhere here. Because I did the complete process, so now I know where they are. And then you move the other ones. And so you get this other wall chain and this other wall chain. So you get from a surface, and here you do the same, moving this other way towards that intersection. And you see, you get 2, 2, 2, 2, and it can blow up. So this is 5, and then you continue doing blow-ups, and you get 6 to 2. And then you recover this part of the chain. So at the end, you get from a picture like this, another picture that has 1. So the contraction of this is this W mark toric, because this is now a toric surface with 1, 2, 3, 4, 5 singularities. And this toric surface is the Pezzo. You can prove that. It is a toric surface. And then from this toric, you can contract this part. So I just want to preserve the original Wahl singularity, that part. And then you will go either to a fake weighted projective plane or a weighted projective plane. And in this case, this is 99 squared. That is the index of this Wahl singularity. And the other ones, I have them. 8, 3, and 4. So more or less you have the picture that you see there with this title. And actually we have a theorem where under certain conditions on a weighted projective plane like this, we can recover the marked surface. And everything, so here you have 3 singularities. One of them is Wahl singularity. The other 2 are cyclic quotient singularities, but with a certain particular property. They admit, here you have they admit F, and this is a negative resolution. Like the P resolutions I was talking about, this is a sort of N resolution, not exactly. And also for this one, but this one is just a Wahl singularity, so it's itself an N resolution. So the cyclic quotient singularities that you get here admit this type of N resolutions, so that you have degrees that are different than 9. You can get 7, 6, 5. Okay, so the theorem and the corollaries, and with that, kind of difficult to explain. But I'm happy to talk about this in case you are interested. So let me write down the precise theorem with my student and then some corollaries so that you can see the connection with Polishuk and time. The theorem. This is me and my student. This is here. So W equals normal projective with only Wahl singularities, and K squared equals D bigger than 0, and minus KW big. Then for each D Wahl singularity in this W, there exists a marked surface with the same singularity of degree D prime bigger or equal than D, so that the blow up at D prime minus D on generic points. When you have the degeneration of P2 with this quarter 1-1 singularity, you can take a generic point, like a generic section, and blow up. And so F1 goes to the same, so a surface with the same singularity, and an extra -1. I think that Porti calls them floating curves. So, and you cannot avoid that on the Pezzo. So we have this blow up, and maybe a certain, maybe you don't need them. I don't know. This mark generating 2 this double. Okay, with this we have a control. I still have 7 minutes. And let me write down some corollaries so that you connect with Polishuk. But also we prove what they prove with hacking vector bundles. But I'm going to tell you only what we have with respect to singularities. So, corollary. There are infinitely many Wahl singularities not allowed in degrees for degenerations in degrees D equals 9, 8, 7, 6, and 5. And for the proof of that, I need to show you are wall chains where you cannot find a marking so that this wall chain is at the Pezzo wall chain of degree bigger or equal than 5. And that is possible, and there are many. I will show you one example. But this is not the only one, there are many. By the way, we have a computer program that is in my webpage called Marks, where if you input a wall chain, then it gives you all the possible markings for all degrees. Just in case. Okay. In English. Language is no, it's Python. It's very simple. Yeah. So by my way, trade is in Spanish. So I thought that you were complaining. A for A bigger or equal than 2 and B bigger than A plus 3. So the idea is you take a situation like that. This is a family of wall chains, and you prove by hand. You need to know certain properties that it's impossible to have degree bigger or equal than 5 without. But the important problem for me is to classify each case like we have for Markov. We know how to think about them, but if you ask me for an algorithm to produce all of them, it's kind of hard. Because you have these Mori mutations, these Markov mutations, and it's complete mess. I can show you a picture. It's like a fractal thing. And just to end, everybody, but this is very simple observation. Everything. So this is kind of theorem B. Although for them, they needed this exceptional collection. And then they said something about exceptional vector bundles. So it's not exactly the same. We don't need any exceptional collection. So everything is possible in degree 4. So that was theorem A for an exceptional collection like this and so on. But the thing is that everything is possible in degree 4, and it's because all wall chains are the Pezzo of degree 4. There is a canonical marking, and there are 2 of them. I will show you how, for example, with that example. That is 2, 2, 7, 9, and then 4. So what you do is the following. There is this wall, Jonathan Wall. Realize how to construct all wall chains, and there is an algorithm that I didn't explain. I didn't explain the algorithm. So there is a central curve. Have you ever seen wall chains in your life? No. Okay, so very good. If you have that this is wall chain, then this is also wall chain. If you flip, it's very simple. But also there is this mutation where you take the first one, add 1, and then E2 up to ER, and you finish with a 2. If this is wall chain, this is wall chain. It's if and only if, the same here. So you start with this, and you can make it smaller, and smaller, using these 2 operations, until you reach the smallest one, which is just 4. And from 4, you get 5, 2, and then you have 2 possibilities, 6 to 2, 2, 5, 3, and so on. There is 3 of them. But everything starts with 4. I have 2 minutes. So this is the position of the 4. This is the center of the wall chain. And then this algorithm tells you how to construct it. See. Okay, so you go like this. Jump this way at the beginning, and then you go to the other side and jump. This is the wall algorithm, and then you finish like this. Okay. The only thing that you need to find the canonical marking is the center and the first jump. So on the center, you subtract 4. On this one, the first jump, you subtract 1. And then you want this to be the center of the construction there, and then you subtract 1 at the end. Or you want this to be the center of the construction, and then you subtract 1. And that always works. And the proof is the wall algorithm. Okay, thank you very much.